Hello, y'all. Today we're going to be going over optimization problems for business calculus, which I really enjoy teaching because you see kind of some practical application of why calculus matters, how it's useful. And this is kind of like the related rates unit where there's multiple kinds of word problems, but they have a similar flow, but they're all different. So the idea here is we're going to assign a variable to each, a letter to each variable mentioned in the problem. Then we're going to find an expression for the quantity that's going to be optimized. And then you're going to possibly substitute into that equation. And then you're going to take the derivative to find the optimization problem. So I'm going to actually explain this with this example to make more sense. Find the dimensions of a rectangle with an area of 108 square feet. So I like to call this the constraint function, and that's just kind of a term that I made up when teaching this several years ago. So you always have a constraint function. That's the thing that's not changing. So in this case, and I'm going to draw a rectangle so we can give some variables here. How do I find the area of a rectangle? X times Y. Now, X times Y must be 108. This is the constraint. It is always going to equal 108. That's not going to change. But what's going to change is the perimeter, and we're trying to minimize the perimeter. And so how do I express the perimeter of this rectangle? It would be X plus Y plus X plus Y. So 2X plus 2Y. This one I'm trying to optimize. So it's not equal to any number because it's going to change. So what you do is you use the constraint function. So use this to substitute into this. So you just have one variable because your goal is to have an equation in terms of one variable. So you can take the derivative to maximize or minimize that equation. So I got xy equals 108, so let's solve for y. It doesn't really matter which one you solve for in this case. Sometimes it's more helpful to solve for one of the variables, like it's just easier to do that. But in this case, it really doesn't matter which one you want to solve for. I'm just going to solve for y. So that means that my perimeter equation, instead of saying 2x plus 2y, I can say it's 2x plus 2 times 108 over x. So 2x plus, if I double that, would that be 216? I'm going to write it as x to the negative 1. Now, anytime you want to optimize something, we're going to take its derivative. If you've seen the movie Transformers from a very long time ago, Optimus Prime is one of the main Transformers. And I think he's named that way, maybe because when you optimize something, you find its prime. You find the derivative. Remember, because the derivative is the slope. And if the slope is 0, we can pinpoint those maxes or those mins because it's a possible turning point for the function. So we're going to take the derivative to optimize the function. So we get 2 minus 216 x to the negative 2 because we're doing the power rule here, subtracting 1. And we want to set this equal to 0. Again, we're trying to find the places where it has a max or a min. So we get 2 minus 216 over x squared equals 0. So just add that to that side, multiply across. So you get 2x squared equals 216. So x squared equals 108. So x equals plus or minus the square root of 108, which doesn't make sense to have negative for this particular problem. So it's going to be the positive square root of 108. And if we want to make that a little nicer, let's see, 108 divided by 2 would be 54. Divided by 2 would be what? Let's see, 2, that'd be 4, 1, set 27. So 2 root 27. That is x. And we want to make sure we answer the question. It says find the dimension. So we found x is 2 root 27. If I want to find y, I need to figure out what y is by plugging in here. It's going to be 108 divided by the square root of 108. But if you optimize, you can multiply by 108 over the square root of 108. And so we get 108 root 108 over 108. So it's also the square root of 108. So essentially it is a square, which if you're going to optimize a rectangle and it has 4 sides, it's always going to be a square. So that is that. Let's solve a different one. A company manufacturer sells X digital cameras per week. The weekly price, demand, and cost equations are given here. What price should the company charge for the cameras? How many cameras should be produced to maximize the weekly revenue? What is the maximum revenue? Okay, so how do I find revenue? Well, revenue is X times P of X, because it's how many you sell times the price each camera is. So that'd be X times 400 minus 0.4X. So that'd be 400X minus 0.4X squared. If we're trying to optimize this, we're going to take the derivative. And I get 400 minus 0.8X equals 0. 0.8x divided by 0.8. So 0.8 into 400 would be 50. So 5. Yeah. No, 500. Oh man. What am I thinking? You 50 and then you add a 0 because you got to move the decimal over 1. Okay, so 500. All right. So we now have that X is 500. What price should the company charge for the cameras? So how many cameras? This is how many. The price would be 400 minus 0.4 times 500. So 200. So 200. And what is the maximum revenue? So the maximum revenue would be multiplying those together. So multiply, so that would give you 10 with 1, 2, 3, 4. So $100,000 is the maximum revenue. Now, what is the maximum weekly profit? How much should the company charge for the cameras? How much cameras should be produced? Okay, so how do you find profit? Remember, profit is your revenue minus your cost. So I have revenue was the 400x minus 0.4x squared minus parentheses 2000 plus 160x. This is your profit function. So 400x minus 0.4x squared minus 2000 minus 160x. So that would be 240x minus 0.4x squared minus 2000. That is your profit. Now, how do we find maximum of anything? Anytime we want to optimize something, we must take its derivative. So just remember Optimus prime. Take the derivative, so we get 240 minus 0.8x. That goes to 0. We set this equal to 0 because, again, we're trying to pinpoint that maximum. So 240 equals 0.8x divided by 0.8. I think it should be 300. 300. And then we answer the question, what is maximum weekly profit? How many is 300? The profit, we just plug in 300 into this equation. So it's 240. 300 minus 4.4 times 300 squared minus 2000. So what is that? 240 times 300 minus 0.4 times 300 squared minus 2. So $44,000. And how much should we charge? So that's the price, 400 minus 0.4 times 300. So 400 minus 0.4 times 300, 280. So we didn't get quite the same cost if we were just maximizing revenue versus maximizing profit. So that's an interesting experiment to go through and conduct. But again, anytime you're trying to maximize something, the idea is get an equation in terms of just one variable and then take the derivative and set it equal to 0 to find those flat places, right? The slope is 0 at a min or a max. And the management of the Unico department store has decided to enclose 800 square foot area outside the building for displaying potted plants and flowers. One side will be formed of the external wall of the store. 2 sides are constructed of pine boards. The 4 sides will be made of steel fencing. The pine board fencing costs $6 per running foot. This still costs $3 per running foot. Determine the dimensions of the enclosure for minimum cost. Okay, so we have a building. And then we have these 2 sides here. They're going to be made of wood. And then you have this side that's going to be made of steel. So say I call this X and I call these Y. So I know that my constraint is this right here, which is area, not perimeter. So you have to be careful because sometimes your constraint will be the opposite. Sometimes your constraint will be the perimeter, like you have a certain amount of materials. But in this case, we know that XY has to be 800, is not going to change. No matter what, you want the area to be 800. Now, what's changing is the cost, and you want to minimize the cost, which of course makes sense. So it says $6 per running foot for the pine board. So that is going to be, how much pine wood do I have? I have Y here and Y here, so that would be 2Y. And then you're going to be multiplying that times the $6 per the square foot. I mean, per foot, sorry. And then plus, you had just 1X, you're going to multiply that by the $3 per foot. So if I wanted to simplify to have one cost function, I have 6 times 2, so that's 12Y plus 3X. And I am trying to optimize this one. So remember, use the constraint function to solve for one of the variables. So we're going to solve for Y by dividing by X. And now you can substitute this into here. And so I have 12 times 800 over X plus 3X. And so 600, I'm gonna write over here because we're out of room. X to the -1 plus 3X is your cost. Take the derivative, so -9600 X to the -2 plus 3 equals 0. So 9600 over X squared equals 3, because you can just add this over here. So multiply that across, so you get 9600 equals 3X squared. Divide by 3. So you get 3,200. So yeah, it's not a pretty number of 56.569, or let's see, that'd be 100 times 32. 32 is 8 times 4. That is 4 times 2. So I could say 4 and a 10. So 40 root 2. Okay, so if I want to simplify, it would be 40 root 2. Determine the dimensions. Okay, so that was X. This is 40 root 2. And then if I want to find Y, I plug it in right here. So 800 divided by 40 root 2. 800 divided by 40 should give us 20. So 20 over root 2, or if you rationalize, it would be 20 root 2 over 2, or 10 root 2. And we should multiply those together just to check, and that should give us 800. See, 40 times 10, that gives us the 400, and then the square root of 2 times the square root of 2 gives us 2, so that would give us the 800. So that is my last example that I have in the notes, but I do want to just show you another example. I'm going to pull it up on the whiteboard because I think it's helpful to see what would happen if you were holding the constraint on the perimeter. So say instead that I have a building and that I have a certain amount of fencing. Say I have 800 feet to fence in a rectangle. And we want to maximize the area that's enclosed. And sometimes it's a building, sometimes it's a river. This is a very typical problem. So I could say my constraint is that 2x plus y equals 800. This time your constraint is the perimeter, and we're trying to maximize the area. The key idea I want you guys to know is that you use the constraint function to substitute into the one you're trying to optimize. So here, if I solve for y, simply because it's easier to solve for, I substitute it, I get x times 800 minus 2x. So I get 800x minus 2x squared. And then I'm going to take the derivative. So I get 800 minus 4x, and I set it equal to 0. I get 800 equals 4x, divide by 4, divide by 4. So 200 equals x. And then I want to find y. So y is 800 minus 2 times 200. So 800 minus 400, which gives us 400. So this one would be 200 feet by 400 feet. And that would maximize the area. So I just wanted to show you that example. Again, you come up with an equation that relates the given things. Usually you have some type of thing that's holding constant, and then a thing you're trying to play with to optimize, either minimize or maximize. You use the thing that's constant to substitute in so that you only have one equation in terms of one variable. You simplify the equation, take the derivative of that equation, set it equal to 0, solve for x. And then I will add the last step is to make sure you answer the question, because sometimes the question is, what is x? Sometimes it's what's the dimensions? Sometimes it's what is the price, or what is the cost, or what is the area? So just make sure you actually answer the question that's given. Okay, so as always, attempt your homework, and please reach out if you have any questions. Good luck.